Hello, and welcome to our second introductory video on how to use the SESAmpacity tool for temperature rise calculations. In this tutorial, I'm going to create and simulate a realistic test case to calculate the temperature rise in an underground cable, which should withstand a fault consisting of multiple current levels. Let's begin by launching the application. Open the SES software folder and then double-click on the Tools folder within it. Next, double-click on the SESAmpacity icon to launch the application. It will open on the main screen. From this main screen, click on the Temperature Rise Radio button. One of the new features in SESAmpacity is a table which is used to specify fault data. The first column simply indicates the fault stage number. The second column indicates the symmetrical RMS current in milliamps at its respective stage. The third column indicates the ending instant of the corresponding stage. Please keep in mind that the beginning instant of a stage is equal to the ending instant of the previous one, except of course for the first stage, which does not have a prior stage. For the first stage, the beginning instant is at 0 seconds. The last column indicates either the X/R ratio at each stage or the decrement factor, depending on the selected method. Now, it is essential to distinguish between the two methods. If the X/R method is selected, SESAmpacity allows the user to define faults with multiple stages. In contrast, if the decrement factor method is selected, SESAmpacity will allow only one stage fault because the IEEE standard 80 defines the decrement factor for the fault stages beginning at 0 seconds only. Thus, we will be focusing on the X/R method in this tutorial. The frequency text box is used to enter the frequency of the grid. This field will only be active when the X/R method is selected. The conductor characteristics group determines the physical properties of the material. For this tutorial, we will choose copper annealed soft-drawn 100% conductivity from the drop-down menu. The values in the conductor size section are related to the cross-sectional area of the conductors being studied. This value can either be selected from a drop-down menu on the left or specified by the user in a field on the right. For this tutorial, we will use a 4-gauge conductor size. At the bottom of the screen is a field for specifying the temperature of the surrounding environment, or ambient temperature. This is also the starting temperature of the conductors. Returning to a full view of the main screen, we see that we have completed entering our information in the fault data table and are ready to continue. To do so, we click the Process button. SESAmpacity will present the summary of the results at the lower left of the screen. To see the detailed results, we simply click on the View Report button located in the ribbon near the top of the screen. SESAmpacity will tabulate the input and fault data together with the material parameters. On the bottom of this page, we can see the output of the computations. The temperature rise and the asymmetrical RMS current at each stage are tabulated. Beneath this table, we can see the overall temperature increase and the final temperature of the conductor. SESAmpacity now offers a visualization of the fault current. From the main screen, click on the View Plots button located in the ribbon near the top of the screen. The first graph to appear is a graphical representation of the symmetrical RMS current. A second graph can be viewed by clicking the Fault Current Waveform tab near the top of the screen. This will display the fault current studied in the time domain. The values in the window group near the bottom of the screen are used to zoom in or out on a specific portion of the waveform. For example, if we want to see the fault waveform from -0.5 to 0.5 seconds, we simply enter those values in the corresponding boxes. Note that because the fault starts at 0 seconds, there is no current before that instant. In the Tools group, the Copy to Clipboard button enables the user to copy the plot and paste it to another document. The Reset Zoom button simply returns the plot to its original view. This concludes our introductory video on how to use SESAmpacity to calculate increases in conductor temperature. If you have any questions, please do not hesitate to contact us.